Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 3.35. I skipped to this problem because it was one of the biggest problems in this chapter, and this chapter has tons of problems. I don't think I can go through every single problem, maybe eventually, but like all of these problems are really long, and there's like 80 problems in this chapter. So if you have a specific problem that you're interested in, just let me know and I can take a look at it. Or if you have questions or something like that, just put some questions in the comments or some recommendations, send me an email or something like that, and I'll try and get back to you and help you out with a specific question that you have. Might be easier to go through that way instead of trying to do every single problem in the book. I'll do a few more in this chapter, and then I'll move on to the next chapter if I don't get any requests. But feel free to request anywhere in the book as well. If you're not in chapter 4 or you're before chapter 4, you can request something from chapter 7 or chapter 8 or whatever. Anyway, let's get into the problem. This problem says, in an absorption tower or absorber, a gas is contacted with a liquid under conditions that one or more species in the gas dissolve in the liquid. A stripping tower, or stripper, also involves a gas contacting a liquid, but under conditions such that one or more component of the feed liquid comes out of solution and exit in the gas leaving the tower. A process consisting of an absorption tower and a stripping tower is used to separate the components of a gas containing 30 mole% carbon dioxide and the balance methane. A stream of this gas is fed to the bottom of the absorber. A liquid containing 0.5 mole% dissolved CO2 and the balanced methanol is recycled from the bottom of the stripper and fed to the top of the absorber. The product gas leaving the top of the absorber contains 1 mole% CO2 and essentially all of the methane fed to the unit. The CO2-rich liquid solvent leaving the bottom of the absorber is fed to the top of the stripper, and a stream of nitrogen gas is fed to the bottom. 90% of the CO2 in the liquid fed to the stripper comes out of solution in the column, and the nitrogen CO2 stream leaving the column passes out to the atmosphere through a stack. The liquid stream leaving the stripper tower is the 0.5 mole% CO2 solution recycled to the absorber. The absorber operates at a temperature, TA, and pressure, PA, and the stripper operates at TS and PS. Methanol may be assumed to be non-volatile, that is, none enters the vapor phase in either column, and nitrogen may be assumed insoluble in methanol. Part A. In your own words, explain the overall objective of this 2-unit process and the function of the absorber and stripper in the process. Okay, so that's super long. This diagram right here kind of shows, this diagram right here shows basically everything they said. So all of the mole components and the streams, like where they're going to and from. So this is the absorber, this is the stripper, and there's a recycle stream. This is the concentration of the recycle stream. There's one gas feed in the absorber, and then there's a gas stream going out the absorber here, stream 3. And then there's a gas feed going into the stripper, that's nitrogen gas, and then the gas comes out here in stream 6. So there's 2 streams in. There's the gas stream in here, and then there's the gas stream in here. And then there's the 2 going out. Okay? And then there's just these this recycle stream, and then there's this stream that, this basically the methanol just kind of gets cycled around, just continuously around and around and around and around and around. It just keeps getting reused over and over again. Okay. Okay, so let's answer part A. What's going in? Methanol plus carbon dioxide and nitrogen. What's going out? Nearly pure methanol and a carbon dioxide nitrogen stream. So what's the point of this process? Looks like methane with no carbon dioxide is the product, or it's the goal. So stream 3. Stream 3 is the product stream. So you have almost pure methanol going out and like a 70%, 30% stream of methanol going in. And then the carbon dioxide over here is just waste. Okay. Part B. The streams fed to the tops of each tower have something in common, as do the streams fed to the bottoms of each tower. What are these commonalities, and what is the possible reason for them? Okay, so the heavy streams go in the top. The liquid streams go in the top. Liquid. And the gas streams go in the bottom. And why is that? Well, because there's a natural motivating force due to the density differences in these two streams, for the gas to rise on its own and for the liquid to fall on its own, right? So the gas and the liquid will just separate. So you don't have to have like a driving force to force, you're not fighting against that natural force of the gas. If you were trying to fight against that natural force, you'd probably lose. So yeah, when you're mixing a gas and a liquid, you want to make sure that you put the liquid in the top and the gas in the bottom, and then they'll just kind of move through each other. Okay. All right, part C. Taking a basis of 100 moles per hour of gas fed to the absorber, draw and label a flowchart of the process. For the stripper outlet gas, label the component molar flow rates rather than the total flow rate and the mole fractions. So here, basically they're saying, hey, don't do it like the way that I did it. And that's wise. When you're solving this, you'll see that I had to do a little bit of a workaround. And if you're not familiar with how to do that workaround, then it could get you stuck. So instead of doing it the way we normally do it, where we've got a mass flow rate and then we've got the mole fractions, just change these variables so that it's like, this is M6N2 or something like that, and then this is M6CO2, right? So then you just have two mass flow rates, but they're component mass flow rates. And then it reduces the number of variables that it doesn't reduce the number of variables you're working with, it just kind of makes it combine certain unknowns, so it makes it a little easier to work with when you're trying to solve some of these problems. The main reason being that M5 is equal to M6N2. So the amount of nitrogen you're putting in the bottom all comes out the top, and so these two things are equal to each other, and then they cancel out. So if you don't see that or you're not aware of that, then it can make it a little more challenging to work with the mass fraction and the components. So yeah, I recommend following what they said because it does make the problem a little bit easier. I'm not used to doing that, and I'm a little stubborn, so I just did it the same way I'm always used to doing it. But you'll see the little workaround that I did in order to fix that problem. Okay, so what else did they say? They wanted to do the degree of freedom analysis and write in order the equations you would solve to determine all unknown stream variables except the nitrogen flow rate entering and leaving the stripper. Circle the variables for which you would solve each question or set of simultaneous equations, but don't do any of the calculations yet. Okay, here's something important that I haven't really discussed yet. There are 7 unknowns for this whole process, But when you do a degree of freedom analysis, you do a degree of freedom analysis around a certain component. So you can do a degree of freedom analysis around the entire process. And there, you could say, well, there are certain components going in, there are certain components going out around this whole process. And then you only have, I'm not explaining this super well, you only have certain components, and you count up the components, and then you count up the process specifications that you have and things like that. But you do that around the whole process. Well, you can do a whole separate degree of freedom analysis, not just around the entire process. You can do one around just the absorber, or just around the stripper, or you could do one around just a mixing point that you have. So anyway, you can do a bunch of degree of freedom analysis. The point is, in this one, you can see I did a degree of freedom analysis around, well, kind of, around, whoa, glitch. I can do a degree of freedom analysis around my material balance of the overall, the absorber, and the stripper, right? And what it turns out, there's not enough, there's not enough material balances that you can do in order to fully specify this problem. So, and they don't give us enough to actually define what the flow of nitrogen is. So this problem is not fully specified, so there are degrees of freedom here. That being said, just because there are degrees of freedom, that doesn't mean certain parts of this problem are not specified or like set in stone. So if I say that the molar flow rate is 100 here, I can find out what a bunch of these other flow rates should be in order to make this, all of these other conditions that we set to be true, without having the problem fully specified. Okay, so that's kind of what they want you to do, is do all of these material balances, do an overall balance, do a balance around the absorber, do the balances around the stripper, use the process specification that they gave to us, and make a bunch of equations. Not all of these equations are going to be independent, obviously, right? Only 7 of them, we have 7 unknowns. We should have 7 independent equations. It turns out we don't, because obviously, like I said before, the problem is not fully specified. So we're writing all of these balances, and we're looking for low-hanging fruit. We're looking for equations where there's like only one unknown, and then we can solve for that unknown, and then maybe that opens it up a path for us to be able to find out what another one of the unknowns are, and do that as much as you can until you kind of reach a wall and you say, well, the problem is not specified up to this point, so I can no longer make any more progress unless I specify a certain flow rate, or I specify a certain concentration, that being the degree of freedom that we're setting. All right, anyway, so I'm starting off with my material balances in the absorber. First I did my CO2 balance, and I said, okay, there's 4 unknowns in this equation. That's too many for me to work with, so I'm going to move on to methane. And look at that. Hey, there's one equation with just one unknown in it. Perfect. That'll be my first one that I do. Then I'll do my balance around my methanol. Methanol is symbolized by OH. Methane is symbolized by Me. Carbon dioxide is CO2. Just to make that clear. All right, so I did my balance around my methanol. All this green writing that I've got on the side that talks about my solving, what I solved for, and things like that. We'll go over that in a little bit. I won't do that right now. I'm just showing you the different balances that I did first. Okay, so then I did all 3 balances that I could around my absorber. Now I'm doing all the balances I can around the stripper. Okay, so now I do my CO2 balance. Then I do my methanol balance. Oh, look at this. This equation is duplicate to what I got up here. Okay, so like I said before, not all of these equations are going to be independent. That doesn't mean you can't do the balance. It just means that you use, for instance, you can't use this equation and this equation to solve, the unknowns that you have, because they're going to have the same unknowns. You'll get something that's like arbitrary, like or totally useless, like 1 equals 1 or 2 equals 2 or something like that. It's just not useful. Okay. Okay, so then we do our nitrogen balance. But there's not enough, like I said before, there's not enough information here to kind of specify nitrogen flow rates. So that's why they tell you don't solve. Solve for all the unknown variables except the nitrogen flow rate entering and leaving the stripper. Okay. I still did the nitrogen balance just so we could see that there's not enough information here. But there is some important information right here where the nitrogen flow rate going in equals the nitrogen flow rate going out in stream 6. So these quantities are equal to each other. So when we go down and we do our overall mass balance, we can see that these things are equal to each other and they'll cancel each other out. The process specification I put in here, that's another variable that we've got, or another equation that we've got that we can use. Then I did an overall mass balance of CO2 and overall mass balance of nitrogen. That's a duplicate to what we had up here before. And then an overall mass balance of methane, which also ends up being a duplicate that we've had before. Okay, so you see these little numbers here that I've got on the sides, the green numbers in green that I've circled. So we've got 1 here, 2 clear down here. Basically what I'm looking for is, like I said before, equations where there's only one unknown. So the first one I did, I was looking through here and I was like, okay, M3, I just solved for M3. Then I looked through and I said, okay, now M3 is known. Does that open up any other options for me? Okay, this is known. M3 is known now. So now there's only one unknown here. Now, like, remember what I said before, where you group this item together like they recommended in the problem. So even though this appears to be 2 unknowns, remember how they recommended that we just combine these 2 things into one variable. So that becomes just one unknown. We're just combining that quantity into a single unknown. Okay, so that's how I write my unknown right there. I just highlighted the whole grouping in one. So I don't know the exact mass fraction, and I won't because I don't know the nitrogen flow. But I do know the actual molar flow rate, or can solve for the molar flow rate of CO2 going out the stack. So, okay, so I solved for that. I took all of these, equation 1, 2, 3, 4, 5, 6. I went through and I put them in order down here, so you can kind of see my thought process going through. So first I solved for methanol, then I solved for the CO2 stack flow, then I solved for the combined flow of the mass flow rate going into the stripper, and the just of CO2, and this is our process specification, okay? Because now I know this quantity, so the only unknown is this one, right? Okay, so now in number 4, I know this quantity now, I know this quantity, and the only unknown is M2, right? So I can solve for M2. Okay, now that I know M2, I can use equation 5 and say, oh, I can figure out what M4 is and kind of break that out, because remember I had it kind of grouped over here in equation number 3. Well, I can use that grouping and then I can solve for M4. Once I know M4 and I know this combined flow rate, then I can use equation 3 and 5 in order to solve for the rest of these. So I can solve for the mole fraction of CO2 in stream 4, and then from there get the mole fraction of the methanol as well. Okay, so that fully takes us as far as we can go with the information that we have. Okay, calculate the fractional CO2 removal in the absorber, moles absorbed per moles in gas feed, and the molar flow rate and composition of the liquid feed to the stripping tower. Okay, so there's a few different ways that you can calculate how much is absorbed. The way that I did it is I said, okay, there's a certain amount of CO2 going out in stream 3, and then there's a certain amount of CO2 that kind of gets added to it that's not getting absorbed in stream 2, right? Because stream 2 is getting cycled around. And so if we're just considering one pass, the CO2 that's in stream 2 is CO2 that did not get absorbed, right? So if I subtract that out of the CO2 that's leaving in stream 3, then I get 98%. The other thing that you can do is you could say, okay, the amount of CO2 that's getting absorbed is the amount of CO2 that's in stream 6. Okay, so if we did stream 6 divided by how much CO2 is going in, which is stream number 1, so if we did stream 6 divided by stream 1, we should get the same thing. Okay, and indeed we do get the same thing. Okay, so there's a bunch of different ways you can calculate this. What you don't want to do is forget to include that there is a certain amount of CO2 being recycled that is not getting absorbed. You need to factor that in. So if you end up with an efficiency that's greater than 100%, you did something wrong. So that's what you don't want to end up with. Okay. Then these are I obviously already calculated these. These are the, I showed those earlier up here in this area of how to calculate those. Okay, so part E, calculate the molar feed rate of gas to the absorber required to produce an absorber product, gas flow rate of 1,000 kilograms per hour. Okay, so now I'm saying the mass flow rate of stream 3 is 1,000 kilograms per hour. I convert to the mass flow rate into a molar flow rate, and I need the molar masses of those components, and then I figure out what the molar mass of stream 3 is by doing a weighted average. So this is the molar mass of stream 3, and then I convert that molar mass into a kilograms per mole, because we are working in kilograms up here, kilograms and moles. Okay, so then I find out what the molar flow rate of stream 3 is. Okay, so then I make the assumption that since these mass fractions were specified, they don't change, right? Because they were specified in the problem statement. So I don't need to go back through and redo a bunch of all this work that I did, because we didn't change anything that wasn't already specified. The thing that does change is obviously the flow rate of M1, and that is the flow rate of M1. Okay. Part F. Would you guess that TS would be higher or lower than TA? Explain. Hint, think about what happens when you heat a carbonated soft drink and what you want to happen in the stripper. What about the relationship of PS to PA? Okay, so here are two things. High pressure and low temperature makes gas go into a liquid. Okay? High temperature and low pressure makes the gas come out of the liquid. Okay? So in an absorber, we want the gas to go in the liquid. Well, that would mean that in the absorber, we want high pressure and low temperature. In the stripper, we want the gas to come out of the liquid. So we would want high temperature and low pressure. Okay, so you kind of flip the two. When you're in your absorber, you have a high pressure and a low temperature, and in your stripper, you have a high temperature and a low pressure. Okay, and the process will kind of fight you on that, because when a gas goes into a liquid, there's a reaction going on. It's more thermodynamically stable, right? So if the gas goes into the liquid, then it's going to release a little bit of heat, right? So you have to keep that temperature low. You have to extract that heat that's being produced. And guess what? You need to keep it at high pressure, right? If the gas is going into the liquid, that means the pressure is going to reduce, right? So you keep that pressure high, you have to continuously provide that extra pressure on that gas, okay? So the process is going to fight you to bring this, to try and maintain these things. And the exact opposite, the same thing is true in the stripper. The gas is coming out, that means the pressure is going to want to increase. And when the gas comes out of the liquid, that's gonna absorb a little bit of energy, and so the temperature is going to want to decrease, right? So you have to keep providing that high temperature. Okay, so it takes energy to maintain these processes, is the point that I'm trying to make. All right, part G. What properties of methanol would you guess make it the solvent of choice for this process? In more general terms, what would you look for when choosing a solvent for an absorption stripping process to separate one gas from another? Okay, so you want high solubility for the component that you're trying to separate, right? CO2, you want CO2 to be soluble in whatever solvent you're using. But you don't want solubility for the two other liquid or gas streams that you're using. So you don't want it to be soluble to the methane or to the nitrogen, right? So you want it to be selective, is what they call it. Okay. Low volatility. You don't want your solvent to be separating, obviously, or like off-gassing or whatever in the different processes. Even if it's not necessarily soluble in these gases, you don't want it to have like a high vapor pressure so that it's like boiling off at, the low pressure conditions that you've got or the high temperature conditions. Okay. You also want it to be stable at the temperature and pressure ranges that you're working in. So that doesn't just go with vapor pressure, that also includes like thermal cycling. Maybe your solvent will, after you've recycled it a few times, it just kind of falls apart and becomes something else, like chemically breaks down over time. You don't want that. What else? You want your you don't want it to like turn into a solid while you're cycling it. So let's say you go to the low temperature and high pressure, and all of a sudden your liquid turns into a solid. It's got to be stable and be in the right phase that you want it to be in the ranges that you want to work in. All right. Well, that is it for problem number 4.35. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.